Hello students. As a result of this video, you will be able to state Le Chatelier's principle. That is the focus of the video. And you will be able to apply Le Chatelier's principle to predict the direction in which a system that is at equilibrium will shift to respond to a stress. So let's dig in. What is Le Chatelier's principle? Le Chatelier's principle tells us that once a system has reached equilibrium, when it experiences a stress, the system will shift in a direction that relieves the stress, but then eventually a new equilibrium position will be attained. So let's set up the situation. So we've been looking at a system in physical equilibrium that has water in the liquid state that is vaporizing, and then some of the vapor is condensing. And so if we took a closed vessel, so nothing in, nothing out, and we understand if we let it set with time, we know some of these water molecules get enough energy colliding into themselves to be able to free the particle attraction and become vapor. And at a certain temperature, we know that water has a certain vapor pressure. So I'm going to make up some numbers. Let's imagine that, we have 1,000,000 water molecules in the liquid state. Maybe at 25 degrees Celsius, maybe we have 50 water molecules in the gaseous state. And it's taken its time to reach this balance. Now, if it is at equilibrium, we know the rate of condensation is equal to the rate of vaporization. So maybe we have 10 liquid becoming vapor, but then at the same time, we would have 10 vapor becoming liquid. That's what it would mean to be at equilibrium, the same rate of change. It doesn't mean the same amounts of reactant and product, but it does mean the same amount is becoming product as product is becoming reactant. Well, what if we would take this system that has taken time to reach this balance and stress it? Well, first, what can be some sources of stress to a system that is at equilibrium? Well, the sources of stress could be a change in the amount of reactant or product. And for our experience, we are just going to exert a stress either on the reactant or the product side. So we'll either be adding or taking away reactant or adding or taking away product. We could also change temperature. We could also change pressure. We could also change volume. Now, changing the volume of the container actually is going to have the consequence of changing pressure. So actually these go hand in hand. So if we kind of, keep these in mind, let's go ahead and focus on this system at equilibrium and let's exert a stress. So let's say that we take away, so the stress is we are going to remove some of the water vapor. Well, if you remove product, then the balance is no longer there. And so the ratio is out of whack. Even if we would just remove, let's say, just a little over half. So let's say that we then have 20. With this temperature, we should have a ratio of 1,000,000 to 50. And so what will happen? If this is our ratio, then the system is going to shift, come out of equilibrium for a moment to account for the stress. So the problem is we don't have enough product. So the response is the reaction will shift right, or we could say favor formation of product, or we could say favor product, or we could say that the rate of vaporization will exceed the rate of condensation. So all of these mean that for a moment, these arrows are not going to be equal. For a moment, a whole bunch of liquid is going to push to form vapor. And of course, you're going to have some of that vapor reforming liquid, but we're going to have it drive. So then, you'll have maybe 999,980. And so you're going to, work to make some more gas. And so we'll have very, very similar to the ratio that we had before. So eventually, we're going to work, and then it can relax and regain equilibrium. But what we have to be able to do is to judge what direction the system will shift when we exert one of these stresses. Okay? So let's go ahead and dig into some more examples. So what if we have, again, that system of liquid creating gas, and it's reached equilibria. We can know that because of these double arrows of equal size. Well, how about the stress that we did before was change amount, and we'll go over some more examples. But let's pursue, what if we would increase temperature? All right. Well, the way that we have to approach this then, okay, if we are increasing temperature, we're adding heat. So in what direction will heat push that side? Or what side needs heat? Well, for liquid to become gas, well, we know we have to add heat. Well, for gas to become liquid, well, we have to remove heat. So one way to approach this is we could actually, write heat as a reactant. We can say we know we need heat to move in this direction. We need to remove heat to move in this direction. So it's endothermic for vaporization, but it's exothermic for condensation. So if we are increasing temperature for this reaction that is endothermic in this direction, then the stress is going to push the endothermic direction. And so the reaction will shift right, will favor product, or we could say the rate of vaporization will exceed the rate of condensation. All right, so for this circumstance, if this is our stress, this is how the system is responding. So whenever you're exerting a stress, you are not always going to shift toward product. You're not always going to shift toward reactant. You're not always going to stress out one side always over the other. So we really have to apply our just understanding of the chemistry that's going on. Let's take sublimation, for example. Okay, so sublimation, let's take water in the solid state and get the conditions so that we're forming gas directly from solid. All right, well, what if we would decrease temperature? All right, what side will naturally form more, if you will? Or we could say, when we're dealing with temperature, here we are removing heat if we're decreasing temperature. So what direction do we need heat? Solid to go to gas. Oh, we need heat for solid to go to gas. In the opposite direction, we're releasing. So if we are decreasing temperature, it's almost like we're removing product. Yeah? We're removing removing reactant. So we know if we remove reactant, the reaction is going to shift in a direction to replace that. Or we could say, well, okay, if we have this imbalance and we decrease temperature, which phase change do we know we're going to encourage? We're going to encourage, if we're decreasing temperature, what would be the exothermic direction. And so for this, the reaction will, or the equilibrium, will shift left, will favor reactant, or the rate of condensation will exceed the rate of vaporization. We could just kind of imagine that, what we would observe is we have, some solid water, and of course, can't see water vapor, but we would see the growth of more crystals of solid in order for this stress to be responded to. So there again, what is the stress and how will the system respond to that stress? All right. What about a change of volume or a change of pressure? So let's just generically say that we have, let's say, how about some liquid methanol, and it is in equilibria with its vapor. Okay, and it's at a certain temperature, so it's worked out its balance. All right. Well, how about if we decrease the volume? So if you imagine we have a sealed container, and my artwork, so I'm just going to draw a box, but we have some liquid in there, and per the temperature, it's gotten its balance, and it's creating a certain vapor pressure at that temperature, and now all of a sudden you've taken the vessel and you've decreased the volume. Okay, well, what is that immediately going to do? That is going to take all those vapor and they're going to come closer together. So we could say that the change in volume affects the vapor. So remember, a change in volume or a change in pressure, it only impacts gases. It's only seen as a stress on gases. Our liquid and our solid state are already compressed. They virtually have no empty space. So you can change the volume and change the pressure on a liquid all day long. It's not going to be seen as a stress. But a gas, well, that's something different. So if we're decreasing volume, well, if we just think chemically what's going on, we're going to cause these to come closer. Now, we could just say, well, that's going to encourage condensation. And so, this gaseous side is impacted. Decreased volume, we're going to increase the pressure. So how do we relieve that stress? It's going to shift left. The reaction will make more liquid so that it can get back the same pressure it had at that temperature when it was a greater volume. So the reaction to respond to the stress will shift left, or we could say, favor reactant. We could say that the rate of condensation will exceed vaporization. So that would be our approach. Now, what if we increased volume? Well, there again, a change in volume is just going to impact the gaseous state. So all of a sudden, whoa, that gas has so much room, but it's not colliding as much as it was in the original container. So we're going to make more gas to replace what seems to be lost. And so in that case, we would shift right. We would be making more product to replenish the vapor that seems to have been lost because of the increase in volume. Or we could say favor right, the rate of vaporization will exceed the rate of condensation, and then eventually the balance is regained. Okay, so we've gone through A change in temperature, a change in volume, which is the same as a change in pressure, and a change in amount. I hope I hit them all, right? A change in amount, a change in temperature, a change in volume, which is kind of synonymous with the change in pressure. Now, can I comment for a second about what is not a stress? You could add something to your vessel that is not actually a reactant or a product. So let's say, for example, that we added inert, so non-reactive helium gas. Well, if we add gas, that's going to change pressure, but it's a different species that's not even involved in the reaction. So that would not be seen as a stress. So even though we wrote down that list of things that, we would say are definite stresses, it could be that you're adding something that's actually not in the chemical reaction. Now we know amongst our friends, different things stress different people. So for example, I'm sure it didn't break your heart that Trolls World Tour wasn't able to premiere in the movie theaters because of the COVID-19 closures. But that I bet made a lot of 6 and 7-year-olds cry. So a stress for one circumstance is not necessarily a stress for another circumstance. And if we're changing pressure, which, if we're changing volume, we're probably doing that. It's not a stress on a solid or a liquid. All right, I'd like to do another short video. Now, if you feel that this was enough and you'd like to try some examples, please look at the examples I have below the videos. But otherwise, in the next video, I'm just going to walk through some sample problems with Le Chatelier's principle. Thank you.